We've all heard the legends about amazing custom knife makers that make knives that cut longer, with edges that don't chip, that are heat treated way better than the production factory knives. Is that actually true? Well, I have a bunch of tests that I performed comparing custom heat treatments to production facility heat treatments, and we're going to go through them and explain why there are differences, how much difference there actually is, and should you care as a knife buyer. And to those knife makers out there, are you too proud of your heat treating? Should you be a little more humble about it and realize that it might not be so different from factory heat treating? So to talk about custom versus factory heat treating, we have to talk about the individual steps of heat treating and what is different between factories and custom heat treaters. So the first major step that we typically do in heat treating is to austenitize. This is starting with annealed soft steel. So the steel is ready for drilling and cutting, etc. Then we austenitize it. That just means heating it up really hot and you soak it for some period of time. Then next you quench the steel, which is rapidly cooling it, usually down to room temperature. Then tempering. This is reheating the steel to a lower temperature than austenitizing, usually something like 400 degrees Fahrenheit or 200 Celsius for 1 to 2 hours. And then you do that 2 to 3 times, cooling to room temperature in between. Then an optional step that can also be added in is a cryogenic or cold treatment. You can do that either after the quench or in between tempering steps or even both. And that just involves cooling the steel to as low a temperature as possible. Now these steps can be performed with a pretty wide range of equipment, and that choice of equipment will have an effect on the results. So austenitizing, when we're heating up between something like 1450 to 2250 Fahrenheit, depending on the steel and the target hardness, which would be about 785 to 1230 Celsius. So you need a specialized furnace to do this. The biggest difference between small batch heat treating done by an individual custom knife maker and a factory is the size of the furnace. So knife makers usually use a benchtop unit such as those made by Evenheat or Paragon. So the number of knives that are in the furnace is usually much greater in a factory furnace. There are pros and cons to both situations apart from the number of knives. A furnace is not perfectly evenly heated. It's going to be slightly colder at the door or in the corners, and there's some kind of thermal gradient between those hot and cold spots. There is a control thermocouple that measures the temperature, and the furnace is constantly adjusting to hit the target temperature. If you're heat treating one knife at a time and that knife is right next to the thermocouple, you can be reasonably sure the temperature the knife sees is very close to what the thermocouple is measuring. With a loaded up furnace, there will be some variation in temperature. Those knives that are close to the thermocouple will be dead on, and the ones far away from the thermocouple may be off by some amount. That can be a few degrees, that can be 20 to 30 degrees plus, which is the difference between the blades in the center and the blades that might be in the corners of a furnace. Custom knife makers do not always use furnaces, however. It is relatively common for knife makers to use a forge, which is relatively uncontrolled, and the goal is to pull the blade after it is heated into the right range. Some knife makers will try to hold a specific temperature within the forge or improve the uniformity of the forge by using a baffle, also called a muffle. This can be as simple as a large piece of pipe. And less common, though still done by some, is to use a torch to heat the edge or the entire blade. Again, this is relatively uncontrolled compared with a furnace. Quenching also varies quite a bit between knife makers and heat treating factories. Steels are rated by hardenability in terms of how fast they need to be quenched. The general categories are air hardening, oil hardening, and water hardening. And air hardening steel can be quenched with pressurized gas or even just cool it in still air. Oil hardening knives are quenched in oil, and water hardening steels are quenched in water. Factory knives tend to use air hardening steels, in part because they are better suited to large batch heat treating, and in part because all stainless steels are air hardening, and stainless steels are more common with production knives. With custom knives, plate quenching has become popular in the past couple decades for air hardening steels. Plate quenching involves placing the steel between two plates, usually aluminum, and the plates draw heat out of the blade. This is faster than sitting in air and also helps maintain flatness during quenching. The most common quenching method for factories is a pressurized nitrogen gas quench. The pressure of the gas is typically rated in bars, where a 1 bar quench would be atmospheric pressure and 2 bars would be double atmospheric pressure. The higher the pressure, the faster the speed. However, this is not the only factor that matters. How loaded up the furnace is will also dictate the quench rate. If many blades are stacked with each other, that increases the volume, and thus it takes longer to cool it down. You can easily imagine how a 4-inch thick block of steel takes longer to cool than a 1/8 inch blade. And if a relatively small number of blades are in the furnace and they are well separated, that will mean a faster quench rate even with the same pressure quench. The heat treaters usually want to load up the furnace as much as possible for efficiency. Slower quenching means that the hardness and toughness is reduced. So here I have a published study on M2 high-speed steel where they tested with a 2-bar, 6-bar, and 9-bar quench in a vacuum furnace. They tested the hardness, and they also tested the toughness with a bend fracture test. With higher quench pressure, both properties were improved. With slow cooling, carbides are precipitated at the grain boundaries. This depletes carbon from the matrix, reducing hardness. And those precipitated carbides are brittle particles, and they reduce toughness, especially since they are present on the grain boundaries. In a study on Udahome Daivar tool steel, they compared toughness between air cooling and oil quenching, so the oil quenching is much faster. They found the same 48 Rockwell C hardness with both conditions, but the oil quench steel had 25% better toughness. They took micrographs of both conditions, and in the air-cooled condition, you can see the grain boundaries. This is because the carbides were precipitating on the grain boundaries, and then they etch as dark grain boundaries, where the oil-quenched microstructure is even and there's no visible grain boundaries. So vacuum furnaces are not the only method used by production knife facilities, but they are by far the most common. One counterexample would be Paul Boss heat treating, which is located at Buck Knives, and they also perform all of the heat treating for Buck. So they use a conveyor belt furnace, and the steel comes out the other side and cools in air. This type of cooling is generally faster than a pressure quench in a vacuum furnace because of how much time it takes to cool down a fully loaded vacuum furnace, as opposed to these individual blades coming out and cooling in air on the conveyor belt. Tempering has similarities to austenitizing in that we are heating the steel to some temperature and then holding it there. The main difference is that tempering is from a much lower temperature, such as 300 to 1050 Fahrenheit, which would be 150 to 565 Celsius. This means it can be performed in less specialized equipment, and less protection from the atmosphere is required because not as much oxidation happens at the low temperature. Though many custom knife makers will use a kitchen oven or a toaster oven, that can lead to more variability than a tightly controlled furnace. In terms of cold or cryogenic processing, there's various equipment that can do that. The simplest is just to use liquid nitrogen in a dewar, and you can dip the knife directly into that. There are fancier setups that will spray liquid nitrogen or cool down a refrigeration unit with liquid nitrogen. There are also refrigeration units that don't use liquid nitrogen, and they can get quite cold, though not as cold as liquid nitrogen. Liquid nitrogen is about negative 320 Fahrenheit, negative 196 Celsius. Dry ice is also relatively common for sub-zero temperatures. It's about negative 109 Fahrenheit or negative 78 Celsius. I have also tested the use of household freezers, which are in the range of like 10 to negative 15 Fahrenheit or negative 12 to negative 25 Celsius. This is not as effective since it isn't as cold. The lower the temperature, the more effective the cold treatment is, though even a freezer can affect the transformation of the steel. Okay, now I'm going to go through examples of data that I have comparing commercial heat treating facilities to custom heat treating in a small shop. So a lot of this data has never been shown before, so hopefully it is enlightening. The first property I want to compare is hardness. So the final hardness of the steel comes from several factors. Austenitizing from a hotter temperature or tempering from a lower temperature usually means higher hardness. Cold or cryo processing can increase the hardness another 0.5 to 3 Rockwell depending on different factors. However, even with the same austenitizing, tempering, and cryo setup, the quench rate will affect the final hardness. This is one of the biggest differences between typical factory and typical custom heat treating. For the MagnaCut datasheet, I measured hardness for a whole range of austenitizing and tempering combinations with plate quenching, and I did that with no cryo, a household freezer, and also with liquid nitrogen. We also sent steel to Peters Heat Treating, which has typical factory vacuum furnaces that use a pressurized gas quench. They used a 2-bar nitrogen gas quench. You can see that the hardness after the pressurized gas quench by Peters is typically 0.5 to 1 Rockwell C lower than when I plate quenched individual pieces. Different steels can be more or less sensitive to these differences. MagnaCut has 2% moly in it, which increases its hardenability, so it is less sensitive to quench rate. However, a steel like AEBL has 0 molybdenum, and thus it can benefit more from a fast quench in terms of hardness. Of course, an oil hardening steel would be very soft even with a high pressure quench in a vacuum furnace. For air hardening steels, I have heard reports of up to 2 Rockwell C difference between a plate quench and a 2-bar gas quench in a vacuum furnace. I also have toughness data for MagnaCut from 3 different heat treaters that use vacuum furnaces, which I have compared against my own experiments with plate quenching. So the 2-bar and unknown pressure heat treaters were targeting the same hardness with the same approximate temperatures. I am not sure for the reason for the discrepancy in hardness. For toughness, both are a similar offset below the plate quench numbers because of the slower quench speed. Presumably, they had a similar quench rate. The slower quench rate led to a reduction in toughness for a given hardness. The faster 10-bar quench also used a higher austenitizing temperature and a higher target hardness, so the faster quench is not the only reason for higher hardness. However, for a given hardness, this heat treatment was closer in toughness to the custom heat treatment using a relatively rapid plate quench. For carbon and low alloy steels, there aren't as many heat treaters that can handle these steels. However, I have examples for 52100 where they were oil quenched in a commercial heat treating facility. And I have that compared with a custom oil quench performed by knife maker Warren Kryko. Because the oil quench is similar, whether it's in a custom shop or in a commercial heat treater, the quench rate is also similar. And so the toughness-hardness balance of the commercial heat-treated 52100 is similar to the custom oil quench performed by a knife maker in their small shop. If you want to be updated right away when I have new knife steel information to provide, please subscribe to the channel and like the video and all of that so that we can spread the word to more people. So I also will have an interview coming up with Bob Shabala of Niagara Specialty Metals where we can talk about the future of knife steel after the bankruptcy of Crucible and all of that stuff that went down. So subscribe and you can find out as soon as I post that interview. One way that custom knife makers will try to make their heat treatments better than factory knives is in forging and thermal cycling of their blades prior to austenitizing. While knife makers typically will claim that forging and especially thermal cycling is for the purpose of refining the grain size, instead the biggest differences are from affecting the carbide structure prior to austenitizing. The steel manufacturers typically want the steel to be as soft as possible for easy machining and grinding by the end customer. The very soft steel is achieved by having a relatively coarse annealed microstructure. If instead the carbides are smaller and the steel is a bit harder in the annealed condition, then the hardness-toughness balance can be improved somewhat. By modifying the normalizing and annealing process called thermocycling by knife makers, you can achieve these results. Though I have articles and videos in the past on thermocycling, normalizing, annealing of various steels. So thermocycling could be replicated to some extent even in a factory setting, but typically the time, logistics, and cost make this less feasible when hundreds or thousands of blades are being produced. So I have a chart here where I have the same 52100 results I showed earlier, but now I overlaid that with some 52100 that my father Devin Thomas forged and thermocycled. So in this case, the toughness was higher for a given hardness in the steel that was thermocycled. And this is because of the change in the carbide structure. Oh, this is published in an old article on my website, which I will link in the description. Some steel manufacturers will have a coarser starting structure than others, leading to differences in how the steel responds to heat treatment. In my prior study on 80CrV2, I found that one steel manufacturer's steel needed significantly higher temperatures than the others to achieve the same hardness. So here you can see the Buderus material is softer for a given austenitizing temperature than the steel labeled Jantz or AKS, which are steel suppliers, getting steel from somewhere other than Buderus. The KSN cycling used my own recommended normalizing and annealing. Though the cycling procedure I performed did not start with forged steel, showing that improved microstructures can be achieved even without forging. Though we found that this resulting hardness difference also lined up with the starting microstructure. So when we looked at the steel under the microscope after polishing and etching, we found that the Buderus material had coarser carbides than the material supplied by Jantz or Alpha Knife Supply, and those were all coarser than the steel that got my KSN cycling, Knife Steel Nerd cycling. The smaller carbide size also led to improved toughness for a given hardness with ADCrv2. So here in this chart, you can see that the toughness was similar for all of the different starting conditions, but the hardness was higher with finer carbides. Thus, the hardness-toughness balance was higher when we started with smaller carbides. So forging and thermal cycling is much more common with simple carbon and low alloy steels, but there are improvements to be had even with stainless steels by refining the initial carbide structure. And I have a video all on this topic. So here I have results for AEBL and MagnaCut where we came up with an optimized annealing procedure for the steel to make it a little bit finer. And we found that we could give a small improvement in the toughness for a given hardness by optimizing that annealing procedure. So even with stainless steels, there is some possibility of improving properties. In many cases, the difference is pretty small between a basic heat treatment and one with more involved thermal cycling. Usually with more complex and dialed-in heat treatments, the potential improvements are small, on the order of 10 to 20%. And when I refer to dialed-in heat treatments, I don't only mean optimizing thermal cycling, but I'm also referring to optimizing the austenitizing temperatures and the tempering temperatures. I have many articles on my website and some videos for various steels, such as when I found that CPM Crewwear has better toughness with a low temperature temper of 400 degrees Fahrenheit or 200 degrees Celsius, despite the fact that the datasheet recommends the high temperature range of 1000 degrees Fahrenheit or 540 degrees Celsius. However, these types of temperature optimizations can be, and sometimes are, done by either factories or by individual custom knife makers. When using complex or fancy heat treatments, the chance of making the steel worse is usually greater than the chances of making it better. I think every buyer should be skeptical of knife makers that are claiming their heat treatments are significantly better, especially without quantitative controlled testing methods that knife makers are unlikely to have access to. And without that testing, they don't know whether they are making an improvement. I have heard many knife makers claim improvements based on changes they made that basically have zero chance of improving anything, and some of those modifications are actually making it worse. For Knife Steel Nerds, I have tested heat treatment changes I was sure would improve the steel, but instead found worse properties. For example, I did a study on rapid heat treating with salt pots. And when I did a rapid 3-minute salt pot austenitize on 1084, the properties were similar to the furnace, but they were a little softer with the same toughness. But I also tried a triple quench, so a rapid triple quench. We would expect the grain size to be much finer and to improve toughness. Instead, the toughness was much worse when I did this rapid triple quench. The grain size was still incredibly fine, but for whatever reason, the toughness was greatly reduced. And if I had to guess beforehand, I would have said this would lead to better toughness, and so would the average knife maker. But without quantitative testing, we don't know what is improving the steel and what is making it worse. So even when knife makers are doing very fancy or specialized heat treatments, they may not be making the steel better. So the examples I've given so far have been about heat treatments where we assume a furnace with well-controlled temperature. There is another common form of heat treating by custom knife makers I already mentioned earlier, which is forge heat treating. Forge heat treating I am not a fan of, and I've said so in many videos and articles in the past. Though several knife makers have tried to argue with me about this. So knife maker metallurgist Juha Pertula, he did an experiment with forge heat treating of 1075 steel, and he found that when he held the steel beyond non-magnetic, it becomes non-magnetic when it transforms to austenite. He held the steel for 1 second beyond non-magnetic, and already the grain size had gone up and the toughness had gone down. When he used ADCrv2 with a small vanadium addition, that made the steel less sensitive to overheating. In my own experiments with forge heat treating, I also found 1084 steel, which is similar to 1075, to be very sensitive to overheating. It is very easy to heat it too hot. And this is very common in custom knives that are heat treated with a forge. So many knife makers have argued with me, said that they can get their heat treatments perfect every time, and about 3 of them have sent me steel for testing. And all 3 times the toughness was very poor with these toughness coupons that I tested. So I do not buy that knife makers can always hit it every time. Maybe some are better than others, maybe some are more consistent than others, but if you want to have dialed in consistent heat treatments, use a furnace, not a forge. And so this is a big problem, in my opinion, with custom knives out there. Whether forge heat treating is better than furnace heat treating is definitely not one of the great mysteries of our day. If you want a good mystery, tell me, why do people like the Dave Matthews Band?
He wakes up in the morning.
There are also many custom knives which are heat treated in the same way as factory knives. Though many custom knife makers do not perform their own heat treating. Instead, they send out to commercial heat treaters. This can be for a variety of reasons. The three most common scenarios are: number one, the knife maker doesn't have the cash for investing in heat treating equipment. Number two, the knife maker doesn't trust himself to learn how to properly heat treat and or trust the commercial heat treater more. Or three, the knife maker works at a high enough volume that a commercial heat treater makes more sense. In these cases, there is unlikely to be much difference between the heat treatment performed on the knives for an individual knife maker and those performed on factory knives, because the heat treating facilities are the same. Of course, the lines are sometimes blurred between custom and factory knives, so knife makers may outsource many steps beyond heat treating. There isn't anything inherently wrong with that. It just means we can't always neatly categorize things into custom knives versus factory or production knives. So many years ago now, I analyzed a set of Catra edge retention data from a major knife manufacturer. I wrote 2 articles about it. Later, I obtained my own Catra tester, and I did a large set of tests on a wide range of steels, which I have also continued to do so. I have had some knife enthusiasts argue that because I was performing my own custom heat treatments that my tests should not be accepted out of hand. Usually this is because they think a steel over or underperformed relative to where they had already decided this steel should be on the chart. To study this, I compared a range of steels that I have tested to those that the knife manufacturer tested in that data set that I analyzed several years ago. So the relative position of each steel was basically the same, with some small variation, whether it was my custom heat treatments in my garage or the knife manufacturer with factory commercial heat treating. However, you will notice that my results were consistently somewhat higher than the knife manufacturer, averaging about 17% better. This is not because my heat treating was superior. Rather, it's due to differences in the design of the blades, the edge geometry, and how the blades were sharpened. The behind-the-edge thickness was greater with the production-made test knives. Also, the knives that I tested were sharpened with an Edge Pro, which keeps the edges very triangular, without rounding. The factory sharpened knife edges instead have a more convex shape, which makes them behave more like an edge sharpened to a more obtuse angle. The factory knives were given a polishing step at the end of sharpening, which is what was rounding those edges some. My knives were sharpened to 400 grit, which is relatively coarse, which gives the steel enhanced slicing edge retention. So again, the polishing step on those production knives is making the edge less aggressive, and it doesn't cut as long in a slicing test like with Catra. So I did a study on this a long time ago. I compared a 120 grit edge to a 400 grit edge to a diamond paste-on strop polished edge, and the more polished the edge, the lower the edge retention was for a slicing test, which Catra is. Another clue as to where the differences are coming from between my custom knives and those factory knives, we can see on this chart. So I have the production Catra knife measurement versus the percent difference between my knives and their knives. And you can see that the higher the edge retention, the less difference was seen, with the exception of Maximet, which appears to be an outlier. So the lowest edge retention steel, in this case 55 Rockwell C420, it cut 50% longer in my testing. That was because of the sharpening and the edge geometry. I do not have a secret heat treatment for 420 that makes 55 Rockwell steel cut 50% longer. I do not. It's not a heat treatment difference. This is just differences in edge geometry and sharpening. To illustrate just how important the edge geometry is, I have a chart here showing a whole bunch of steels versus total edge angle. So if we take the angle that we sharpen on both sides, so 13 degrees on one side, 13 degrees on the other side, that's a 26 degree total angle. And I have highlighted a few specific steels here on this chart. So Aus6, that's a Japanese steel with about 0.6% carbon. If it has a 27 degree edge angle, that's 13.5 degrees per side, it cut about 400 millimeters of cardstock. This matched the performance of CPM 154, which is significantly more wear resistant. It has over 1% carbon. When it has a 34 degree edge angle, that's only 3.5 degrees per side greater. That same 400 millimeter of cardstock is measured with the very wear-resistant S110V with an edge angle of about 41 degrees. If we give CPM 154 a 27-degree edge instead, just like we started with the Aus6, it matches Maximet with a 41-degree edge. So small differences in sharpening can make big differences in the result of an edge retention test. This is why it's very important when we make steel and heat treating comparisons that we have identical edges. Identical. Because if it's 10% different edge, you're going to measure a 10% difference in cutting performance and edge retention, and you're going to say that was because of a difference in heat treating, when in fact it was not. Custom knives are often given thinner edges than factory-made knives. In general, when someone measures superior edge retention performance in a custom knife, it is because of better edge geometry, rather than any kind of super unmatchable heat treatment that you can't get in the factory knives. When a custom heat treatment does perform better with identical edge geometry and steel, it can usually be attributed to higher hardness. In my own Catra experiments, the effective hardness is greater than other changes to the heat treatment that I have tested. So this is unlike toughness measurements where I have found significant differences when I've changed heat treatment variables. With edge retention, it seems to be more about hardness and the steel choice. For another data set that compares the importance of edge geometry and also has a custom knife in it amongst a bunch of production knives, we're going to look at the Quantified Knife Project of Seattle Ultrasonics, where they tested a bunch of commercially available kitchen knives. I performed the Catra test for this project. So we measured the cutting performance of a range of knives, and we also measured Catra. So for cutting ability, it varied almost perfectly with total edge angle. So the more acute, the smaller the edge angle, the better the initial cutting was, which is what we would expect. However, when we plot edge angle versus Catra edge retention, the overall trend with edge angle is still very strong. We only have a couple of outliers. So both of those outliers, the one over 800 and the one over 1,000, are with a steel advertised as FC61, which is a proprietary name. So I have seen speculation that that steel is similar to AEBL or 13C26, which would be surprising because those are relatively low wear-resistant steels, but we had outperformance relative to the total edge angle in these tests. And the rest of the steels, VG10 is higher wear resistance than AEBL and 13C26, and we tested quite a few VG10 knives, and also the lower wear resistant European steel 1.4116 at 56 Rockwell or so, and they all line up on a similar trend line here. The custom knife, however, had blue super steel, and it was at a very low edge angle, so 4 degrees per side, 8 degrees total, really, really acute. And it cut really well, 650 millimeter. When I tested blue super, I only measured 338 millimeters. But that was with a 30-degree edge angle. So the custom knife had an edge geometry that was selected for cutting performance and edge retention. It would also be more delicate and more likely to chip because everything is a trade-off. But the custom knife in this case, it cut better not because of special forging or magical heat treating, but because of the edge geometry. So sharpenability is another complicated subject. In my prior Catra studies, which have included over 50 steels, I have only had significant issues with sharpening a small handful of the knives. This is in part due to the use of CBN abrasives, cubic boron nitride, which makes sharpening even high vanadium steels pretty easy. Instead, the difficult to sharpen knives were from the heat treating, not the steel. Those difficult to sharpen knives had high retained austenite. So we talked about austenitizing. When you heat the steel up hot, it transforms to a phase called austenite. And when you quench the steel, it transforms to the hard phase of steel, martensite. And if not all of that austenite transforms, some of it is left over or retained. So it's called retained austenite. Retained austenite is soft and it can affect our properties. So you can have just on a microstructure scale, on a very small scale, you'll have retained austenite in the steel. And so those difficult to sharpen knives, when you would deburr them, it would leave behind a ragged edge, which wasn't very sharp. So retained austenite can be minimized in different ways. If you austenitize at too high of a temperature, that increases your retained austenite. When you do that in combination with a slow quench speed, and if you skip cryo, then definitely you get excess retained austenite. Both small batch heat treating and commercial heat treaters can have issues with retained austenite. But there are a couple areas where commercial heat treaters are at a disadvantage. One is the slower cooling rate that we've been discussing all throughout this article. Slower cooling stabilizes retained austenite, which makes less of it transform during a cold or cryo treatment. The other issue is that commercial heat treaters often like to perform cryogenic steps in between the two tempering cycles, where cryo is less effective. The first tempering step helps stabilize the austenite just like a slow quench does. They prefer to do it in between tempering steps because the cryoprocessing is less likely to lead to distortion, warping, or cracking. But it is also less likely to benefit the steel. So the cryoprocessing is doing less, and that's why you're less likely to get issues like cracking. So some knife makers that do their own treating will also do cryo in between tempering. So this is not restricted solely to commercial heat treaters. High retained austenite also makes steel behave as if it is softer than it is. So two knives with the same hardness will behave differently if one has significantly more retained austenite than the other. So the steel will deform more easily. It will behave as if it is softer. So the edges will deform more easily, even though it's at the same hardness. So with proper selection of austenitizing temperature and cryoprocessing, retained austenite can be limited to levels where it doesn't affect the performance of the knife. Some steels have more issues than others. For example, I found that the datasheet recommended austenitizing temperature for CPM S110V is very high, probably too high. So any commercial heat treating facility following the datasheet may have too much retained austenite. Some steels like Vanax and LC200N are difficult to heat treat beyond 58 to 60 Rockwell. So the heat treaters are forced to austenitize at the very peak of the austenitizing curve where it is easy to overshoot. So I have a chart here showing Vanax, the steel that's difficult to heat treat to high hardness, and LMAX, the steel that is easier. And I austenitize these for 20 minutes at the given temperature on the chart. Then we did a plate quench, and I used liquid nitrogen cryo, and then I tempered at 300 degrees. You can see that for LMAX, we have a wide range of austenitizing temperatures where we can get 61 plus Rockwell. And if it was higher than 61, we could temper it down to a lower hardness. So temper it hotter and get lower hardness. The range for Vanax to be over 60 or 61 is much narrower. So 1975 to 2000 degrees is the peak hardness, but already at 2025, the hardness has dropped. So where the hardness drops is an indication that we have too much retained austenite. So all of that retained austenite is what is dropping our hardness. So Vanax is very difficult to heat treat to 60 plus Rockwell while also avoiding excess retained austenite. Also, the composition of steel can be slightly different from batch to batch as you receive it from the steel company. And the austenitizing temperature where the peak hardness is will vary with the composition. Also, there's variation in temperature within the furnace and between furnace batches, which means it's usually better to go a little bit conservative. So we wouldn't want to do 2000 degrees austenitizing because we might overshoot in the furnace, or a batch of the Vanax may be on the rich side, which would shift the austenitizing hardness curve down. So usually it's better to go a little bit lower temperature. So we would use something like 1975 rather than 2000, maybe even a little bit lower. Because even at the peak hardness, sometimes we are creeping up into the regime where we have more retained austenite than we would prefer. So as you can hopefully tell, there is a lot of experimentation that we've been doing for Knife Steel Nerds, testing different heat treatments and steels and all of the different properties so that we can all learn and benefit. The reason why I'm able to do all of that without going bankrupt is because of the support of Patreon. So Patreon supporters come and they get to see articles and videos early. They get certain perks like free mugs at the highest tier, but also by pooling that money together, I use all of the money for experiments. The experiments are expensive, and we can learn about steel together, and I can present all of that information on YouTube and in articles and in books in the future. So if you are interested in supporting knife steel research, please come join us on Patreon at patreon.com/knifesteelnerds. So corrosion resistance, I'm just going to hit on briefly. So again, the carbides precipitated during a slow quench are the thing that is most detrimental to corrosion resistance when it comes to the equipment that we are using. So those carbides precipitate out, and they are chromium carbides typically. So it's taking chromium from the matrix of the steel, and you need that chromium in the matrix so that at the surface it can form the chromium oxide. That's what makes stainless steels stainless. You get free chromium at the surface, and that forms with oxygen to make a protective chromium oxide layer on the surface. Now, other heat treating variables matter apart from the quench speed. So a higher austenitizing temperature means more chromium carbide is dissolved, putting more chromium in solution. And it is relatively common in industry to use the high tempering temperature range, which I've mentioned a couple times before so far in this video, but not too much. So that high temperature range is like 950 to 1050 Fahrenheit, 510 to 565 Celsius, and that high temperature tempering range reduces corrosion resistance. So in my testing of Vanex, comparing a 400 degree Fahrenheit temper and a 1000 degree Fahrenheit temper, and then I sprayed it with 1% salt water, the high tempering temperature Vanex corroded. I got rust spots all over it, where the low temperature tempering Vanex was completely clean. So it turned the Vanex into a super high corrosion resistant steel into something that behaves more like your average stainless steel. High temperature tempering can be used by both custom knife makers and production facilities, but commercial heat treating facilities I have found are more commonly using it, and I have heard about more examples of companies using this in factory settings than by custom knife makers doing their own heat treating. In many cases, the knowledge of the person performing the heat treatment is more important than the equipment being used. A heat treatment without any issues gives you 90 to 95% of the potential performance. It is when there is some problem with the heat treatment where the performance is noticeable to the end user. I have written about this in an old article I wrote called What a Good Heat Treatment Can and Cannot Do. When a knife maker or a knife company outsources their heat treatment to a commercial heat treater, they typically ask for a target hardness and leave it up to the heat treater. The commercial heat treater presumably has significant experience with heat treating, especially with obtaining consistent results, avoiding catastrophic issues, and with troubleshooting common problems. However, many heat treatment facilities lack metallurgists, and when it comes to measuring properties, the hardness test is by far the most common. As I have shown multiple times in this article, hitting the target hardness is only one tiny piece of the puzzle. Some heat treatment facilities are better than others, however. When it comes to custom knife makers doing their own heat treating, the level of knowledge varies widely. Of course, it goes without saying that the average knife maker is not a metallurgist. In general, I would say that the average knife maker has knowledge of the basic steps of heat treating, but their knowledge of the mechanisms behind each step is relatively poor. I reacted to knife maker explanations of heat treatment in an earlier video. If the knife maker knows how to heat treat correctly and how to follow a datasheet, they are usually fine. It is when they are trying to diagnose issues or to modify the heat treatment that they get in trouble without knowing how things work in the steel. I have a video about the basic steps of heat treating and how to follow a datasheet for those knife makers that want to learn. For those that want to learn more about what is happening in the steel and how to modify heat treatments for different purposes, I have many articles on my website and several videos on YouTube and my book, Knife Engineering. So there are a few knife makers that have put in the time required to understand heat treating and gained hands-on experience to become well-informed, excellent heat treaters. So they are often the exception rather than the rule. So this video is too long already, but I did want to mention specialized heat treatment techniques that are used almost exclusively by custom knife makers. One is developing a hamon, which is often for artistic purposes rather than strictly performance. Usually to develop a hamon, you need to use clay, and it's a very individual thing, like you're doing it on one-off knives, or maybe a group of 5 or 10 knives. It's really hard to do this in some kind of factory setting. Other types of differential hardening can also be used, usually only by custom knife makers, and it is less likely to see these in any factory-made edges. So you can do things like edge quenching or tempering back the spine. Both of these are to have a hard edge and a softer spine. These are famously done to pass the 90-degree bend test required for journeyman smith or master smith performance testing. So we went over a lot for this video. I'm going to try to summarize some of the major points.
Let me explain. No, there is too much. Let me sum up.
One of the biggest differences between commercial and custom heat treating is the quench rate. The slower quench rate in many vacuum furnaces used by knife production facilities and commercial heat treaters can often lead to a reduction in hardness and toughness. A faster quench that can be accomplished with other equipment gives better properties. The degree to which this matters can be debated, but there is a potential for small batch heat treating to be superior. The potential for improving edge retention with heat treatment is somewhat overhyped, in my opinion. Hardness is the main area where edge retention can be improved, and this can generally be achieved with commercial heat treating. The biggest differences between good and bad heat treatments come when there is a problem in the heat treatment. It is the heat treaters who can avoid these problems and diagnose them when they come up that perform the best heat treatments. Thanks for watching. Until next time.